public does not have a very good awareness of the science side of NASA. They see the aeronautics work that's being done, they see the space missions that we fly, but there's a whole side of NASA that's engaged in studying the entire planet, looking at the surface of the planet, looking at the atmosphere, looking at the polar regions. Some of the goals are to understand why the climate is changing, why the ice caps are getting smaller, why some years we have more hurricanes than we expect.
To achieve its Earth science mission, NASA employs a wide range of aircraft, each with unique capabilities, allowing the agency to deploy a broad range of science instruments almost anywhere in the world. One of these aircraft is the Globalhawk, an unmanned aerial vehicle developed by Northrop Grumman.
The Globalhawk aircraft has a unique combination of characteristics. It will fly payloads as far as 11,000 nautical miles. It will fly payloads as high as 65,000 feet. The aircraft can carry up to 2,000 pounds of payload. So when you combine all of those factors together, the Globalhawk provides capability that no other aircraft in the world can provide to scientists. One of the first things we had to do to make these aircraft useful for the science community was to figure out how would an instrument be mounted on the aircraft, how would we talk to it while we're flying, and how would we bring power to it.
Development of the power and information infrastructure for science instruments on board the Globalhawk fell to the remote sensing engineers at the University-affiliated Research Center, or UARC. Working in collaboration with colleagues at the NASA Ames Research Center and NASA Dryden Flight Research Center, UARC engineers set about tackling the challenges of designing power management, instrument control, and science data transmission systems for the aircraft.
The Master Payload Control System, or MPCS, is a power control system that switches power to all of the experimenter interface panels throughout the aircraft that the actual experiments are attached to. So it's basically their wall plugs, and it gives them their on and off, and it also gives them GPS signal and time signals from the aircraft. Even though the Globalhawk appears to be a very large aircraft, there is not really as much space as you would think to put components inside. There was a lot to cram into it as far as we had to make the computer as small as possible, we had to make the relays as small as possible, and also the Iridium was a bit of a challenge because that's a fairly new concept, the Iridium satellite phone systems, and it's becoming very widespread, but you have to be very careful with cable lengths and all that.
In addition to power management, GPS, and time information, remote operations require instrument operators to be able to control their equipment from hundreds, even thousands of miles away. To enable this, engineers turn to the same Ethernet technology that allows computers to connect to the Internet.
With an Ethernet protocol being established on the aircraft and on the ground, we literally have instrument owners back in the payload operations room that are sitting there with a laptop or a computer communicating to their instrument as if it's a static IP address on a local area network in the room next door. And the airplane could be 4,000 nautical miles away. And they literally are communicating with their instrument, they're getting data from the instrument as if it's on a local wireless network.
In order for instrument data to be passed between the Ethernet network on board Globalhawk and scientists on the ground, data must be transmitted through the aircraft's Ku-band satellite communications system. Connecting these two systems is the responsibility of the data link controller.
It's basically a computer, a moderately powerful computer that's been hardened to go on an airplane and survive the environment there. It's an intermediary between an aircraft network that all the experimenters' instruments are connected to, and then satellite communications equipment that maintains a two-way communication between the ground and the airplane.
The advanced science capabilities of the Globalhawk platform make it a perfect complement to other airborne remote sensing aircraft. During the recent GRIP mission, NASA scientists sent the Globalhawk into Hurricanes Carl and Earl to gather new information about how these monster storms behave.
Well, GRIP stands for the Genesis and Rapid Intensification Processes Experiment. We're basically looking for how storms form and how they rapidly intensify. While the track forecast for hurricanes has improved quite a bit over the last couple decades, our ability to predict storm formation and intensity still lags quite a bit. And so this experiment is really geared toward getting observations that might help us understand the physical processes better, and also to improve the actual numerical models that are used for forecasting.
With its unique capabilities, Globalhawk is an important asset in NASA's Airborne Remote Sensing program, providing scientists with the ability to gather data critical to improving our understanding of Earth's complex ecosystem.